go. So the nature of ALEKS is such that each student may have a slightly different course of work that they're going to do based on how you do on that initial knowledge check. So some people obviously have taken Chemistry 100. So if you took Chemistry 100, there may be quite a few of the Chapter 3 topics that you already know how to do, and you're able to show it in that initial knowledge check. And if that's the case, then what it'll do is it will kind of move you along to some of the more advanced topics. Whereas if you haven't taken Chem 100 and you don't have any chemistry background, the first problems that you work on might be very basic, just like calculating molecular mass, that sort of thing. So it will vary from student to student. But by the end of the course, I think there's 108 different topics by the end of the course. The goal is for everybody to get up to those 108 topics, okay? So yesterday we talked a little bit about balancing equations. We looked at sort of the simplest type of equations to balance, but today we're going to look at a slightly more complicated looking balancing equations, and then we'll get into a couple of other topics here. Are there any questions, any problems that anyone's done that they had questions about? I do want to prioritize questions if people have them. Okay. All right. So what I'm going to do then is I'm going to go ahead and take a look at a problem. This one is right out of ALEKS about how we balance equations. So let me see if I can pull this one up here. So this one is, it's interesting because they, you know, what they will do, what the authors of these problems will do is they will represent things in modified ways, which then just add another level of complexity to the problem. So I'm going to show you how to deal with that for this problem here. Okay, this is a combustion reaction. We'll talk about combustion reactions a little bit later. There we go. So let's remind ourselves a little bit about balancing equations. The goal is to make sure that we have at the end the same number of atoms of every element, of each element, on both sides of the equation. And there are states of matter that are often shown in here. So for example, actually it looks like every substance in this equation is a gas. We see the little G there, that means gas, right? So everything here is a gas. Now, one of the things that makes this a little tricky is the way they're representing this reactant. This reactant is called octane. N-octane, it would be called normal octane. And they're showing you a little bit of the details of the structure of the molecule. So you see how you have those CH2s in the middle there, 6 CH2s. That's just a notation that allows them to show you what the structure of the molecule is, if you have experience figuring that out, and doing it in such a way that it doesn't take up so much space. So what I'm going to do before we balance this equation is I'm going to condense this formula into a more manageable shape. And so if you take a look at it, there's only 2 elements in that compound. There's carbon. There's a bunch of carbons in there, right? There's 8 carbons if you think about it. There's 1 here on the end, 1 on the other end, and then there's 6 CH2s. So that means there's 6 carbons in there. So if you add up all the carbons, 1 on either end and the 6 in the middle, you have 8 carbons. So it's perfectly fine just to write this as C8. Okay. And then you can do the same thing for the hydrogen. So for the hydrogen, you have 3 on the left side over here, 3 on the right side, so that's 6. But then you've got 6 of these CH2s. Well, each CH2 has 2 hydrogens. So 6 times 2 is 12, plus another 3, plus another 3, so it's 18. So that would be C8H18. And this would be a perfectly, reasonable way to represent the formula for this compound, normal octane. And it makes it more manageable for balancing. So you don't have to like write out the whole thing and then kind of go through each step. So what I'm going to do is I'm going to complete the equation here. And now we have more room also. That's another advantage of it. There we go. Okay. So now we have a manageable equation. So one thing I will say about this one, when you see an equation that has more than 2 elements in it, so this one has 3, it's most likely that that equation is going to be an example of what we call interfering coefficients. And we talked a little bit about that yesterday, meaning that when you balance one element, it affects another element, at least one other element. So we call that interfering coefficients. And we saw that with that iron equation yesterday. So let's try with this one. What I would recommend when you have more than 2 elements in an equation, it's often the case that one of the elements, you can find it all by itself. So for example, right here, see how that oxygen's all by itself? So what I would do is I would say if you have 3 or more elements and one of them, there's some place in the equation where it's all by itself, do that one last, do that element last, okay? And really the issue is interfering coefficients. What happens is if you balance the carbon and the hydrogen first and you leave oxygen for the end, then you can put a coefficient here to balance the oxygen, and that's not going to affect anything except the oxygen, right? So what you're doing is you're eliminating the interference that occurs when you try to balance one element and it's connected to another, okay? So just do the oxygen last. Generally, most people, when they do combustion equations, they do the carbon first, then the hydrogen, and then the oxygen, but you don't have to do carbon and then hydrogen. You could do hydrogen and then carbon, but you do want to leave the oxygen for last because it's all by itself, okay? So let's go through. I'm going to start with the carbon. And so on the left side, there's 8, right? So for the carbon, you've got 8 on the left side. Let me actually write this a little bit further down. So let's do this. We got 8 carbons on the left. On the right side, you've only got 1, right? It's just CO2. So again, one way to deal with that would be to say, look, we have more on the left, fewer on the right. Let's make more on the right, more carbon dioxide, more carbon on the right. And so we do that with the coefficient. Remember, we don't change the subscripts, because if you change the subscript to C8O2, you would create something that doesn't exist in nature. So the subscript is fundamental to what the material is. For example, CO is carbon monoxide. That's a poisonous gas that will kill you. CO2, 1 carbon, 2 oxygens, is carbon dioxide. It's a different material that you can breathe out, and plants need it to make glucose. So we don't change the subscripts. We change the coefficient. So if there's 8 on the left and 1 on the right, let's just multiply the right side by 8. And the way we do that is with the coefficient, right? So the 8 that we're multiplying by is the coefficient. So that now gives us 8 on both sides. And then the next one would be hydrogen. And on the left side, we have 18. That's a nice big number. And on the right side, we have 2. So again, there's more on the left side than there is on the right side. So we got to multiply that H2O by something to give us 18. So, arithmetically, what you would do is you would say 2 times something, 2n, is equal to 18. And so n would be 18 over 2, and that would be 9. So that means we got to multiply it by 9. So we put a 9 there. Now notice that's what we would call an interfering coefficient, because that 9, not only does it change the number of hydrogens, it also changes the number of oxygens. So it's changing 2 different elements. So there's an interference occurring there. But because we left oxygen for the last step, we're in good shape. And here's why. We have this O2 over here that we can put any coefficient we want. And when we put that coefficient there, it's not going to affect the number of carbons, and it's not going to affect the number of hydrogens. Whereas any coefficient here, that affects 2 elements. Any coefficient here affects 2 elements. Any coefficient here affects 2 elements, but this one doesn't. So we've now turned it from an interfering coefficients into non-interfering coefficients, which are the easiest ones to balance, like 4 N2 plus H2 gives you NH3, 2 elements, very simple, okay? So now let's do the oxygen. Now we have to be careful with the oxygen because there's oxygen in 2 of the products. So let's just make sure we get the numbers right. There's no oxygen in the N-octane, in the C8H18, but there's 2 on the O2. And then on the product side, you've got, be careful, you have 8 times 2, right? So it's like bicycles. If you have 8 bicycles, you have 16 tires, right? So that's 16 right there. So 8 times 2. And then you've got 9 waters. Well, there's 1 oxygen in the water, so that's 9. So you got 16, that's 25, right? So now we have an interesting issue, which is it's 25. So let's go through and figure out how to change this coefficient, just like I did with the hydrogen. And so here's what I would do. I would say, look, the only thing on the left side we can change is that coefficient in front of the oxygen. So let's do this arithmetically. There's 2 oxygens, so 2 times the coefficient, 2n, right? N's the coefficient, the number we're going to put in front here. That number has to equal what we have on the right side, the product side, which is 25. We've already calculated that. So to figure out what that number is going to be, we just divide both sides by 2. So N, is 25 halves. And there you go. So now I've written a bunch of stuff in here, so let me erase that N up here and make a little more room for myself. Now this is 25 halves. And at first glance, that looks sort of odd because now we have a fraction. And many instructors of chemistry will tell you that fractions are a no-no in balanced equations. And many textbooks will actually tell you that as well. And even ALEKS, my understanding of ALEKS problems, they actually want you to get rid of these fractions. So I'm going to make my own sort of editorial point here, which is that there is nothing wrong with fractions in balanced equations. They're perfectly acceptable. And chemists use them all the time. In fact, there are advantages to using fractions over whole numbers in balanced equations, and it's often preferable to use balanced equations. However, we do have the issue of technology, and we do have the issue of textbooks. So what we would do is we would say that in general, when we represent balanced equations, we generally do try to eliminate the fractions in the coefficients, or fractional coefficients. No reason to do it, to be honest with you. And even the programmers at ALEKS could certainly develop a software program to deal with fractions. Fractions to computer processing is no more difficult than dealing with whole numbers. But for some reason, this is often done in freshman chemistry. So what we're going to do to eliminate the fraction, meaning the 25 halves, is just multiply by the smallest number possible that gets rid of the fraction. So if you have a fraction that's a half, some multiple of a half, like a half or 3 halves or 5 halves, all the way up to as many as you want to go, for example, 25 halves. Multiplying that by 2 eliminates the fraction. So 2 times a half is 1, 2 times 3 halves is 3, 2 times 5 halves is 5, 2 times 25 halves is 25, and that eliminates it. So the issue you have to deal with, though, is that if you multiply this 25 halves by 2, that changes the number of oxygen atoms, right? You go from 25 halves to 25. So you also have to get this up to 25 on the right side. So the way you deal with that is you don't just multiply the fraction by 2, you multiply everything by 2, okay? So that gives you 2 C8H18 plus 25 O2, 16, right? I'm just multiplying everything by 2, and then 18H2O, okay? And again, that actually, I almost feel apologetic for it because, to be honest with you, the idea that you don't have fractions in there is ridiculous. You can have fractions in a balanced equation, but it's just the nature of the software that they're going to want you to get rid of the fraction. So just multiply everything by 2. And then when you multiply everything by 2, that doubles everything. So everything will still be balanced. You know, if you have 25 on the left and you have 25 on the right, if you double that, it's still the same, 50 and 50. It's got to be balanced. Okay. Let me see if I can show you one more. Let's see, let me bring this over here. Because, you know, you're doing an additional step here. Yeah, let's try this one. This is an interesting one. This one's an inorganic reaction. So this one is SiH4. This is called silane. Oops. Yeah. Sorry, I got the I did the formula wrong. Sorry. Si4H10. So that's a liquid, and we're going to balance it with oxygen. And that's going to give us SiO2, silicon dioxide, which is the component of glass and sand. And then H2O liquid. Okay, there we go. So same thing. This one might work out to be interfering coefficients as well. So let's take a look at it. Again, if you have 3 or more elements, what I recommend is look for one of the elements that's all by itself. It's isolated, right? See you have the O2 there all by itself. Do that one last. And then the order of the other elements doesn't really matter. You could do the silicon first. You could do the hydrogen first. Generally, what I do is I go left to right. So the first element I see is silicon, so I would do that first. So let's try that one. So I'm going to come down here, Si. So on the left side, there's 4 of them, right? And then on the right side, there's only 1. So that means we got to multiply the 1 by some number to give us 4, right? So 4 times 1 is 4. So I'm just going to multiply that by 4. And now we've got it balanced. So the way we multiply it again is the coefficient. You put it up here, the coefficient on the left side. Okay. So now we have 4 silicon dioxides. Okay. This is often referred to as the law of conservation of mass, meaning that if you have 4 silicon atoms at the beginning of the reaction, you have to have 4 silicon atoms at the end of the reaction. So let's do the hydrogen next. So on the left side, you got 10. And then on the right side, you only have 2. So again, you got to multiply it by some number, right? So you know, mathematically, the way you could do this, you could say is like, look, 2 times some number equals 10. So if you divide both sides by 2, you get 5, right? So that means we got to multiply by 5 to get 10. And you just put that as a coefficient. Again, the numbers in the front are the coefficients. We don't change the subscripts in balancing equations. And then that just leaves us with oxygen. And again, this is an interfering type problem because you have oxygen next to silicon and oxygen next to hydrogen. But because we did the silicon and the hydrogen first, that leaves the oxygen all by itself right here, and we can just balance it right there. Okay, so let's go through. On the left side, we have 2, just like we did in the previous problem. And then on the right side, 4 times 2, right? So 4 times 2. And then over here, 5 times 1. So that's 8 plus 5 is 13. So just like the previous one with the N-octane, we have an issue where it's probably going to be a fraction, right? Because we got to put a coefficient here, some number there that times 2, so 2n, has got to equal this number on the right side, 13. So if 2n equals 13, that means you divide both sides by 2, and that from that, n is equal to 13 halves. So now we know what that fraction is there. And that's actually a balanced equation. That's a perfectly balanced equation. But to eliminate the fraction, we just multiply by 2. So you get 2 Si4H10 plus 13O2 4 SiO, I'm sorry, 8 SiO2 and 10 H2O. So in a sense, just to connect it to what I was talking about yesterday, this idea of multiplying by 2 to get rid of the fraction, in a way, it's connected to the issue of the diatomic elements. Remember I talked about that yesterday? I said that there are 7 elements that are diatomic in nature. I'm just going to list them here again, just as a reminder. Sometimes we need reminders of things. So those are diatomic. So what happens is the reason that we have to multiply, in a sense, the reason we have to multiply by 2 is because oxygen is a diatomic element. It's not O, right? So if oxygen were a monatomic element, if it was just O, right? It'd be easier to balance. It'd be a lot, I mean, not a lot easier, but a little bit easier to balance, right? Because you would balance the silicon and the hydrogen just like we did. And then you'd say, hey, we got 13 over here. So we would just put 13 there. And we wouldn't have to worry about the fraction. But what happens is in nature, these elements are diatomic. They don't exist as monatomic elements. They exist as diatomic elements. It's an interesting aspect of these nonmetals. And because of that, that means that instead of being 13, it's 13 halves, which then leads you into having to multiply the whole equation by 2. So it'd be easier if it was like that, but it's just the nature of things. It isn't like that. This is the structure of these elements. Okay. All right. Any questions about balancing equations? Let me see here. Go back to Kayla. For the first problem, you got rid of the fraction by multiplying the entire by 2 and putting brackets. So the brackets, yeah. So you can change, no, you can't change, well, okay, let me be careful. Be careful with the terminology every number. So the reason I put brackets there was just to kind of be consistent with mathematics, to say, look, I'm multiplying everything by 2. So I forget what it was, just 13 halves. 9H2O. So I just put brackets there, like that's not a requirement of balancing it. It's just I'm just trying to show that mathematically I'm multiplying everything by 2. Now I think you're right. I just want to be careful when you say double every number. Just be careful. We don't mean these numbers, right? We're not going to double those numbers. We're just doubling the coefficients. So just to be more technical about it, exactly. Coefficient, right? So what you could do is you could say, look, I don't need to put those brackets there because I know what I'm doing. And you know, that's perfectly fine. So you would say, look, I recognize I got to get rid of that fraction, so I'm going to multiply by 2. So I'm just going to put 2C8H18 plus 13O2 plus 16CO2 and 18H2O. Yeah. So you don't have to put the bracket there. Good. Excellent. Good question. Okay. All right. So let's take a look then. And again, reach out to me this week if you have any problems with the balancing equations. Let's take a look at the next issue, which is balancing equations, but this is now going to be balancing equations where they give you a word problem. And this is, you know, generally it's considered a slightly more advanced topic. It's really the same issue, but it's just a matter of converting words and names into chemical formulas. Okay, so the one I want to show you, again, I'm going to probably for this semester focus mainly on ALEKS problems because those are the homework problems that you're doing. And I just find it helps people better to do it that way. So aqueous study. So this one is called writing a chemical equation. From a description of the reaction. So if you remember back in the 3rd grade or 4th grade, when you finally got those well, they do it now earlier, they do it like in kindergarten now, but when you would get those word problems, so suddenly you had to convert words into a mathematical equation. That's essentially what we're doing here. We're going to convert these words into a chemical equation. Okay, so an example of this would be aqueous sodium chloride. And aqueous sulfurous acid. That's cool. We'll talk about acids in chapter 4. Are produced by the reaction of hydrochloric acid and sodium sulfite. Oops, sodium sulfite. So they give you the formulas of a couple of these or a few of them. But not all of them. You know, actually it's just sodium chloride. They don't give it to you, but I guess they assume you know sodium chloride, right? So sodium chloride's NaCl. So really what you're doing here, oh, did I get the states of matter? So everything's aqueous. Yeah. So I'm just going to put in here, everything's aqueous. I left it out in some of the in there, but everything in there is aqueous. Okay. So aqueous sodium chloride and, so remember, and is plus. So in a chemical equation, and is plus. So aqueous sodium chloride and aqueous sulfurous acid, which is H2SO3, are produced. So that means those are the products. And in a chemical equation, the arrow points toward the products. Usually the products are on the right side and the reactants are on the left side, but there is no rule that the products have to be on the right side. It just generally they're written that way, but the arrow points toward the products. That's the notation that we use. Convention, they call that. So aqueous sodium chloride, so NaCl. And then again, aqueous, all that means is it's dissolved in water. We'll talk about ions in chapter 4, and we'll talk about what the meaning of aqueous sodium chloride is. And then aqueous sulfurous acid, which is H2SO3. Again, AQ for aqueous. So those are the products, and they're produced by the reaction of aqueous hydrochloric acid, and they give you the formula for that, HCl. And then they give you the formula for sodium sulfite, Na2SO3. Again, it's aqueous. Everything's in there. It's aqueous. Okay, so we're halfway there. We don't have the balanced equation, but we've at least written, it could actually, in theory, it could be balanced. It doesn't look like it is, but in theory, it could be balanced, okay? Now, this one, and if you're doing one of these problems and you just don't know what the chemical formula is, just Google it, type in the words and find what the formula is, and you'll get it pretty quickly. So when you're doing these problems, this one, it has several elements in it. It's got hydrogen, chlorine, sodium, sulfur, and oxygen. It's actually got 5 different elements in it. So there's no way out of this being interfering, meaning changing one element is definitely going to change at least one other element. So let's figure out how to go about this. I'm going to make a little table here and list all the elements. NaSO, yeah, that's all 5. Okay, so on the left side for hydrogen, we have 1, and on the right side, we have 2. For chlorine, we have 1 on both sides. That's cool. For sodium, we have 2 on the left and 1 on the right. And then for sulfur, it looks like it's 1 each. And then for oxygen, it looks like it's 3 and 3. So actually, it looks like some of them are balanced. It looks like the only one that's not balanced, the only 2 are hydrogen and sodium. So if we're lucky, this equation might work out that we can balance it relatively simply, right? Meaning, you want to avoid changing sulfur and oxygen if you can, because they're already balanced, and you want to avoid balancing changing the chlorine, but it turns out you're gonna have to change at least one of these. So let's go through it. So I'm just gonna start, when I balance equations, to be honest with you, I just start on the left side and move to the right. That's generally what I do. So I'm gonna start with the first element, hydrogen. There's one on the left and two on the right, right? So that means if we put a 2 here, if the coefficient is a 2, that'll balance the hydrogen, right? Just put a 2 there and that'll balance the hydrogen. The problem with that is that now we have 2 chlorines, okay? So here's what I'm gonna do. I'm gonna move on to the second element, which is chlorine. So chlorine, there's 2 of them, right? The coefficient refers to everything in the formula, so the hydrogen and the chlorine. So if I've got 2 chlorines over here on the left, I need 2 on the right. So let's just multiply that by 2. Okay. Now what has that done? That's now made it 2 sodiums on the right. But here's the nice thing about that. That actually fixed the sodium, right? Now there's 2 on both sides. We actually have a balanced sodium. And sulfur's already done, and we didn't affect sulfur. Oxygen's already done. We didn't affect oxygen. So we're done. We finished this one already, okay? So again, what I did, just to review, I started on the left side. I looked at the first element that wasn't balanced, and it just turns out that the first element on the left wasn't balanced. So I balanced it first, the hydrogen. Then I just kept in check. Okay, changing the hydrogen is also changing the chlorine. So I had to take that into account, that we now had 2 chlorines. And then I balanced the chlorine. I did the second one on the left. Then I moved over to the third one. And that one was already balanced, right? Because when I put the 2 for the chlorine, that actually balanced the sodium. So in general, when you do these writing chemical equations from a description of the reaction, most of them are not so difficult. They're not going to give you, one of these ones where you've got 5 elements and you end up with coefficients of 6 and 7. Like there actually are equations that you have to balance where there's like 5, the coefficient's 8. I've seen 8. And they can be really like you have 3 products. So some of these equations, you have 2 reactants and 3 products. And to get them balanced, you have a coefficient of 8. Those are pretty tricky, hard ones. But for these ones where you're writing a chemical equation from a description of the reaction, they're most likely not going to give you one like that. I haven't seen them give any like that. That would be, they're in textbooks and you see them a lot, but you're not likely to see that one in here. So let me show you one more. This one's actually even easier to balance. But again, really what we're doing in this type of problem is we're not learning how to balance really hard problems. That was the previous problem, the interfering coefficients. This one is more just about translating. Think of yourself as a translator here. You're taking names and you're converting them into equations, right? So it's like a word problem. So this is another example. This one says ammonia gas. And often when you read questions in chemistry, sometimes they'll put the word vapor instead of gas. And that just means the same thing. A vapor is the same thing as a gas. So if you see that vapor, it just means gas. So ammonia gas is obtained by the reaction of nitrogen gas and hydrogen gas. So really all you're doing here is you're sort of getting, oh, they don't tell you what ammonia is actually. So, there are a few compounds you should know their formulas. Like the most common ones, of course, are water. Ammonia is actually one you should know. It's in I think it's in chapter 1 of your textbook. They give you the formula of a few of these. Carbon dioxide. These ones you should know. And the other one was sodium chloride, those 4. Okay, so the reason they give you ammonia is because it's just a common material. So really all you're doing here is you're just trying to figure out, the balancing is going to be simple. It's going to be easy to balance this one, but you're just trying to figure out how to get these words into a sentence. I mean, into a chemical sentence. So let's take a look. Ammonia gas, so ammonia is NH3, is obtained. So there's the trick right there. It is obtained. That means you're making it, right? If you're making something, it's a product. Right. So that's just the issue of the English language. So that means you're making ammonia. So our product is NH3. And it is a gas, it's a vapor, so G. And then we got nitrogen and hydrogen by the reaction of nitrogen and hydrogen. So those are the reactants, right? We're reacting nitrogen and hydrogen to make ammonia. But here's the trick for that one. Remember the diatomics, right? I'll put them up again. H2, N2, O2, F2, Cl2, Br2. So when someone says that nitrogen reacts, what they mean is N2. When they say that hydrogen reacts, they mean H2. If they said sulfur reacts, you would just write S. If they said phosphorus reacts, you would just write P. But if it's one of those 7 elements, you want to use a diatomic. So nitrogen and hydrogen. Okay, so there's the equation. And now the last step is just to go ahead and balance this equation. So let's take a look. You got nitrogen, you got hydrogen, we got 2 and 1, right? 2 on the left, 1 on the right, and then 2 on the left and 3 on the right, right? So here's what I'm gonna do. Again, I generally just start from left to right. So the first element I see is nitrogen. There's 2 on the left side. So I'll multiply the right side by 2. Okay, so you put a 2 there. Again, that's a interfering coefficient. So now you have more hydrogens, right? So now you got 6 hydrogens on the right, right? 2 times 3. And so now we need to have 6 over here. So times N equals 6, right? We want these to be equal. You want the same number of hydrogens on both sides. So what does N have to be? Let's write it this way. 2n, right? Because there's your 2. So 2n has got to equal 6. So you divide both sides by 2, and you get n equals 3. So that means our coefficient here is a 3. And there we go. So we have a balanced equation. N2 plus 3H2 gives us 2NH3. And they're all gases. We got the states of matter. What we would call stoichiometry. Stoichiometry, that term refers to the coefficients. The coefficients are 1, right? That's the coefficient of 1. Even though there's nothing written there, the coefficient is really a 1. The coefficient there is a 3, and the coefficient there is a 2. I've seen multiple choice exams where what they would have you do is they'd have you do this problem, and then they would say, the sum of the coefficients in this equation, in the balanced equation, is 4, 5, 6, 8, 10 as a multiple choice. And then you would just circle a 6, right? Because you have to add those up together. But in ALEKS, what they're going to have you do is write the equation. And so you got to be good. The thing about ALEKS, you got to learn how to use their interface for subscripts and for superscripts when you get to ions. In chapter 4, we'll do ions, so you have to do superscript. But for chapter 3, balanced equations, you have to get good at doing the subscripts. Okay. So there you go. So there's a couple of examples of those. Again, the writing the equations, they usually aren't the difficult ones to balance. It's just more of testing your ability to translate the language of English into chemical equations. Okay. So let's see, close that one. And then that gets us, we've had about 20 minutes. So that gets us into now the next topic, which is a fun one, which is called using Avogadro's numbers. So let me write this down. This is in section of your textbook 3.4, and the section 3.4 is called the mole and molar mass. Now we're going to get into counting. We did a little bit of counting yesterday when we talked about counting the number of atoms in a balanced equation on one side of the equation. We're going to do a different type of counting here. Here, what we're going to be doing is we're going to count from the mass of a substance. So we weigh it. We're actually going to be able to count the number of atoms that's in that substance. So for example, in theory, if I had, a little piece of paper here, there's a certain number of carbon atoms, a certain number of hydrogen atoms, and a certain number of oxygen atoms in here. So what we would want to be able to do is to count the number of carbon atoms in this piece of paper, count the number of hydrogen atoms in the paper, and count the number of oxygen atoms in the paper, and nitrogen. There's probably nitrogen in here too as well. So that's really what we're doing now, is we're saying, hey, I'm going to weigh something, and then from that weight, figure out how many atoms are in that substance. Okay. So it's a little bit more involved, but let's take a look at it. So that's in section 3.4. And so what I'm going to do is I'm going to go over a problem which is called using the Avogadro number. Okay. And before I actually do this problem, I just want to give you what the number is. The symbol for Avogadro's number is typically an uppercase N with a subscript A, usually uppercase, so NA. Sometimes it's N, but usually it's NA. And the number is, I'm only putting 4 sig figs. It actually is more than 4 sig figs, but I'm just going to stop at 4. Okay, so it's 6.022 times 10 to the 23rd. There are different definitions. There's different working definitions of Avogadro's number. And there's different meanings to it in a sense. So I'm not going to focus on whether it's the number of carbon 12 atoms in 12 grams of carbon. What we're going to do is we're going to say it's really just a large number. It's just a large, useful number for counting atoms and molecules. And this is something that we do in our everyday lives, not as much as people used to do, but we do it a little bit. So for example, when you buy a dozen eggs, we don't say, hey, go out and buy 12 eggs. We say, go out and buy a dozen eggs, right? So a dozen is like sort of a bundle of something. So that's 12, right? Same thing with pairs. We wouldn't say, can you go out and buy 17 socks? What you would do is you'd say, well, look, you got to buy socks in pairs. So could you buy 8 pairs of socks, right? So I'm trying to think. I suspect if you went into Target and you bought some socks in a package, it's going to give you the number of pairs, right? It's not going to give you the number of socks. So, 1 pair equals 2. There's other units of counting as well. There's something called a gross. There's something called a score. There's other ones as well that I don't want to go over, but there are many of these bundles, we could call them, for counting numbers, okay, just to make it more convenient. So what happens is, because atoms are so small and there's so many of them, right? Like the number of atoms in the universe is like 10 to 100th, right? 10. So that's 1 followed by 100 zeros. That's a large number. So even in your body, there's 10 to the 25 or 10, about 10 to the 25 atoms in your body, right? 1 followed by 25 zeros. That's how many atoms in your body. So what happens is counting atoms in terms of the actual number becomes inconvenient. So if I said, can you go out and buy 3 million eggs? That would be inconvenient. So we have other units that we use for counting. And so one of them is this Avogadro's number. And what I'm going to do is I'm going to give it a name. So it's called Avogadro's number for historical reasons, but it's also the same thing as 1 mole, M-O-L-E. Okay. So that is going to be the most useful aspect for us in this course, is that relationship right there. 6.022 times 10 to the 23rd of anything is a mole. So if I had 6.022 times 10 to the 23rd stars, and as I go through the calculations of the known universe, it's not that far off, really. The number of stars in the universe is probably about a mole. It's probably about 10 to the 23rd. It might be 10 to the 21st. It might be 10 to the 25th. But, when you're getting up to numbers that big, it's somewhere around 10 to the 23rd. That's probably how many stars in the universe there are. As I said, in the human body, there's more than that in terms of the number of atoms. It's probably about 10 to the 25th. So here's what you would do then. You would say, like, look, if I had twice as many, if I had 12.044 times 10 to the 23rd, right? So all I did was I multiplied it by 2. You would have 2 moles. I'll put an S at the end, right? So yeah, now you have 2 moles, right? So it becomes a useful number if you're dealing with large numbers of things. And let me show you another example. So suppose I said I have 0.6022 times 10 to the 23rd. Grains of sand, for example, on the earth. Right, so what did I do? I just moved the decimal point over to the left by 1. So I made it 1/10. It's 1/10 the value of what it was. Well, that would just be 1/10 of a mole, right? 0.1 moles. And so this unit, the mole, is really what's useful for us. This number, this unit right here. So the mole, if I say I have 1 mole of carbon atoms, what I mean is I have this number right here. If I say I have 0.1 mole of water molecules, 0.1, right? Not 1, but 0.1, so 1/10. So now I would say I have 0.6022 times 10 to the 23rd, right? I multiplied it by 1/10, so I made it 0.6022. So what it becomes is a very useful number for counting large numbers of objects, of particles, or whatever you want to call it. So if I want to know how many electrons are in the human body, how many electrons does a human body have? Well, it's probably 10 to the 26th. Well, 6 times 10 to the 23rd is a mole. So it's probably like 1,000 moles. There's probably 1,000 moles of electrons in the human body. And that's more convenient to say than to say 6 times 10 to the 26th. It's easier to say 1,000 moles than it is to say 6 times 10 to the 26th. Okay. So that's the real purpose from the chemistry perspective, is that it becomes like a unit of counting, just like the dozen is for eggs. 3 dozen eggs, 3 moles of carbon. 60 pairs of shoes, 60 moles of water, And just to estimate it here, this is probably about 100. I don't know, it's actually probably about 180 milliliters of water. I guess that's about 180 milliliters. So that's about 180 grams. So that's about 10 moles. Seems like a lot, right? 180, yeah, I guess that's about 10 moles of water. So it's a convenient, the mole is convenient for figuring out how much substance you have. Well, that's about right. Okay. So let's take a look at a problem here. All right, so using Avogadro's number, what it says here is that now this particular problem is a little tricky. We got about 10 minutes, so this is about right. So it says an oxygen atom has a mass of 2.66 times 10 to the minus 23rd grams. Okay. And a glass of water has a mass of 0.050 kilograms, kg. Okay. And then they want you to answer a couple questions. So one is, what is the mass of 1 mole of oxygen atoms? And then how many moles of oxygen atoms? So notice they're very explicit here. They're not saying oxygen molecules or oxygen. They're saying oxygen atoms. So that's a way of telling you don't do O2. If it just said oxygen, you would do O2. But if it says oxygen atom, then it's just O. Okay. So how many moles of oxygen atoms have a mass equal to the mass of a glass of water? So the first question here is pretty basic. The second one, you have to do a little bit of reasoning. It's not really a difficult chemistry problem. It's just you have to kind of think logically. So let's take a look at this one. Part 1, or A if you want to call it that. What is the mass of 1 mole of oxygen atoms? Well, again, 1 mole is 6.022 times 10 to the 23rd of anything. So it could be oxygen atoms if you want it to be oxygen. It could be cats if you want it to be cats. That would be heavier. It could be electrons. It could be photons. Okay. In fact, there's a unit called an Einstein, which is 6.022 times 10 to the 23rd photons. We'll talk about photons in chapter 6. Okay. So here's the logic. We know how much 1 weighs. So if we had 2, you would just multiply it by 2. If you had 10, you would multiply it by 10, right? So if I said, 1 car weighs 2,000 pounds, how much does 10 cars weigh? Well, 10 times 2,000, 20,000 pounds. So same thing here. You would say, look, it's 2.66 times 10 to the minus 23rd grams per oxygen atom, per 1 oxygen atom. You don't have to write out explicitly like this when you're doing it, but I just want you to kind of see the logic and the notation that I'm using. So then you would say, well, how many oxygen atoms am I weighing? Well, it says a mole, right? Well, how many is, how much is a mole? A mole is this number right here. So 6.022 times 10 to the 23rd oxygen atoms. Again, I'm being explicit about the units here. There's this idea of dimensional analysis where you can cancel units. So that's what I just did right there. Okay. So let's see what we come out. Let's see what this big number is. Well, you got a really, 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 really small number, 10 to the minus 23rd, times a really, really, really big number, 10 to the positive 23rd. And so the 10 to the minus 23 times the 10 to the plus 23 are actually going to cancel and give you 10 to the 0, which is 1. But you can just use your calculator for this. 2.66 times 10 to the minus 23rd times 6.022 times 10 to the 23rd, and you get 16.0. And then there's our unit of mass, which is the gram. And there you go, 16 grams. Okay. There you go. So that's part A. So that one's pretty basic. It's just saying, look, this is how much 1 weighs. How much does 6 times 10 to the 23rd weigh? Just multiply it by that number. Now, notice in the second question, it's a different unit. It's not in grams, it's in kilograms. So let me show you the conversion between grams and kilograms. Kilo, or K, is called a prefix. is equal to 1,000. Kilo is 1,000. So make sure not 100. Hecta is 100. Not 1,000th. Milli is 1,000. Kilo is 1,000. So when we say 0.050 kilograms, okay, that's really 0.050 kilos 1,000. So times 1,000 grams. So 0.050, 1,000 grams. So what happens when you multiply 0.050 by 1,000? Well, you move it over 3 places. So it becomes 50. So this is now 50 grams. Okay. Another way to do that conversion would be kind of more formally, which is you would say this, 0.050 kg. I'm converting it into grams. So you would say, look, it's 1,000 grams per 1 kilogram. So 1,000 times 0.05 is 50. So you get the same answer that I got before, right? Just a slightly different way of doing it, okay? So now a glass of water has a mass of 50 grams and 1 mole, remember this is 1 mole of oxygen atoms. And they were very explicit about saying oxygen atoms as opposed to oxygen. So that's 1 mole. So how many moles are in 50 grams? So 50 grams equals how many moles of oxygen? Right? How many is that? Well, I mean, think about it in terms of counting. 1 mole is 16 grams. 2 moles would be 32 grams. 3 moles would be 48 grams. So you know your answer is it's over 48, but it's 50. So it's a little bit more than 3 moles. So here's how you could do it. You would say for oxygen, it's 16.0 grams is 1 mole of oxygen. That's what we did in part A. So I'm going to write it as this equation right here. It's called an identity. And then I'm going to say, okay, here's what we have. We have 50 grams of water. So how much oxygen is that? 50 grams times 1 mole of oxygen is 16.0 grams of oxygen. So see what I did here? I put the mole up here at the top, and I put the grams down at the bottom. And the reason I did that is because grams cancels, and now you're going to get moles. Okay, so that again, that's what they call dimensional analysis. So it's going to be a little more than 3. So 50 divided by 16 is 3.1. So it's 3.1 moles of oxygen. Okay. And let's check. Let's just make sure. Because we know it's 16 grams. There's 16 grams in 1 mole. And if we had 2 moles, that'd be 32 grams. If we had 3 moles, that would be 48 grams. So 50 grams would be just a little bit more than 3 moles. And that's exactly what we got. Okay. So that is, again, that's the ALEKS problem called using the Avogadro number. Okay. What's today? Today's Wednesday. So great. So tomorrow, what I would like to do is to look a little bit more at using moles, and we're going to do molar mass. And so we're going to work more on this section of 3.4, but it might help you if you could at some point today start working on these problems, kind of do section 3.2. There's no problems from section 3.1. But 3.2, 3.3, and get into the mole, and then that will help you tomorrow when we come back and we talk a little bit more about section 3.4. Okay. So I'm going to go ahead and put this on to YouTube. It should take me an hour or 2 to get this up on YouTube. I'll post the link into Blackboard. And question about ALEKS. Every day there's an assignment. So there is. It's not like you have to do the problems today. It's a range of times. So all the problems from chapter 3 on ALEKS need to be done by, I think it's next Friday. I think it's a week from this Friday. You'll want to check on the ALEKS calendar, but I think I made all of the due dates for the homeworks on Fridays. And so it's not like you have to do, in theory, you could do them all next Thursday and Friday. I don't recommend doing that because doing 20 different types of problems in 2 days is just going to overwhelm your brain. So I do recommend you try to do 3 types of problems each day. But, obviously you're taking other classes and you're probably working and you're probably taking care of someone and you have to shower and work out and cook your meals. So there might be a day or two during the week where you just don't have time to work on chemistry. But I do recommend you try to do a few problems each day. And that way you just don't get overwhelmed at the end. Because if you get overwhelmed at the end, it just won't work. But yeah, so just look at, I think each chapter is set up for a Friday there. So why is it just grams and not grams per mole? So let's see. That's actually a good question. So let's be a little bit more explicit. So per mole. So really what we did was we took this conversion factor. 1 mole is that. And then Junhao, I'll answer your question in just a second. So what did we have? We had 2.6. Okay, here we go. So that's gram per 1 atom. So technically you're right, because really what it is it's 6.022 times 10 to the 23rd atoms per 1 mole. You're right, because we're using this one right here. So it's really this divided by that. So then your oxygen atoms cancel. And so it's really grams per mole. Very good. So there's a little bit of an issue of how we interpret the meaning of the question. So for example, it says, what's the mass? The mass is 16 grams. But if it is 1 mole, you're right. 1 mole is 16 grams. So in my mind, either answer would be correct. You could say 16 grams because in the question it says 1 mole. But technically, you're right. It's 16 grams per 1 mole. Okay. Should we? Yeah. So you got to do that initial knowledge check before it even lets you do any homework. It's going to lock you down on that initial knowledge check. And it's set up to where you can't access the ebook. So what I would just say about the initial knowledge check, try to take 30 to 40 minutes to do it. Try not to spend more than an hour. I have had students like Google answers and stuff on the initial knowledge check. And what happens is if you spend 2 hours and Google things and really work it out without really understanding it that well yourself, it then just puts you into a different, like the stratosphere in terms of the difficulty. It gives you harder problems to work on because, all this will give you the harder problems. So just be kind of honest about it. If you really don't know how to do the question, just say, I don't know. And if you do know how, do it. Because the ones you do know how to do, it eliminates them from you having to do them, so you won't have to do them on homework problems. But if you don't know how to do it, be honest about it and say you don't. So you got to do the initial knowledge check first. Take 30 to 40 minutes, and then once that's done, then you can work on the homework. The more of the homework you do, there will be little tabs up the top that you can click on, and you can work on. It gives you more freedom over time. You'll have more freedom to work on the problems you want to work on. Because sometimes you're like, I don't want to do this problem. I want to do a different type. And at the beginning, it doesn't really give you very much freedom. It says, look, you got to work on this problem first. But over time, once you do them, the little tabs will become available, activated up at the top. And then that gives you a little more freedom in terms of which ones. Because I know for me, I might feel like doing this kind of problem right now, and I don't feel like doing that one. But over time, that'll happen. Okay. So again, I'll put this up. Reach out to me if you have more questions. And if you haven't used ALEKS, it's a completely different system than you've probably ever used. So don't feel bad if you're getting confused about it. Just reach out with questions and I'll get back to you, okay? And have a great day. Today's Wednesday, so I'm going to have another lecture tomorrow at 9. And if you can make it, that's great. If you can't make it, I'll post it onto Blackboard. So have a great day, everybody.